I'd like to welcome you today to our webinar, Making Smart Solar Site Assessments. And before we begin, I would just like to go over a few house cleaning items here. I'd like to mention that this webinar will be available after the presentation on solarpowerengineering.com. The webinar will also be emailed to all attendees. Also, there will be a question and answer session at the end of the presentation, so you may submit your questions at any time throughout the webinar by typing it into the GoToMeeting panel, which I believe should be on your right. Lastly, we realize that not everyone who would have liked to attend this webinar could, so we encourage everyone to tweet about key topics and takeaways using the hashtag SmartSolar. All right, and at this time I'd like to introduce our presenters. Today we have a nice panel of site assessment experts, including Dr. Bruce Bailey. He is President and CEO of AWS TruePower. We also have Gwen Bender. She's Project Manager at 3Tier. We have Peter Hoberg. He is VP of Sales and Marketing with Solmetric Corporation. And Stacy Fleenor is Resource Modeling Analyst with WinLogic. So thank you all again for being here with us today. And so Bruce is actually going to be our first presenter. He has been active in the solar and wind industries for 30 years. He's published and presented over 100 papers on resource and energy assessment, project design, performance assessment, and forecasting. He holds degrees in meteorology and engineering management and is a certified consulting meteorologist. So we're very glad to have him with us today. And Bruce, please take it away.
Thank you very much. My topic will be on solar resource assessment and dealing with measurement issues as well as expectations of financiers of solar projects. I might first mention that AWS TruePower has been providing renewable energy consulting services to the solar and energy sectors for the last 25 years. We're headquartered in Albany, New York, but we also have offices in the Americas, Europe, and in Asia. Topics that I'll be covering today. There's three topics. First is the importance of solar resource assessment. And this is applicable to developers as well as investors. Secondly, best practices for on-site monitoring. And this is to ensure high-quality data and low uncertainty. And lastly, conducting an investment-grade analysis that is consistent with the expectations of investors. So why does solar resource assessment matter? Well, the fundamental answer, of course, is that you need to accurately understand the energy source before you can make a well-informed investment decision. Solar resource assessment has implications for such things as site and system design, also for long-term energy projections and understanding the variability in the output of your system, and also in quantifying uncertainty of your output projections. Investors are interested in high-confidence energy estimates, and they tend to look at what's called a P50 energy prediction for a solar project, or a P90. P50 is sort of the 50-50% probability that your output will be over or under a particular number. P90 is a 90% probability that you'll experience at least a certain level of annual energy output. And it's the P90 that is the more important one, typically for investors. There are a variety of data sources to define the solar resource for a particular site or a particular region. Modeled data, these are data that are generally available from public or private sources. A commonly used one is the U.S. National Solar Radiation Database. It's available from the National Renewable Energy Laboratory. And model data sets are derived either from satellite imagery or from numerical weather prediction models. And these data sets are generally intended to provide guidance on geographic and seasonal patterns of the solar resource, and also to support siting activities. Generally, model data are not intended for final system design or for investment decisions. Another type of data source are sort of regional, ground-based solar radiation measurements. These may consist of National Weather Service stations, research facilities, and in general, these types of data sources are few and far between, sort of widely scattered around the country or in other parts of the globe, and quality levels can vary from station to station as well. And then finally, the most ideal type of data source is on-site measurements, and that's what we're focusing on today. And these deal with measurements that are tailored to the specific needs of the user, but also they tend to be relatively short-term in nature and need to be correlated with some other data sets in order to derive long-term energy production projections. There are a variety of advantages and disadvantages or weaknesses and strengths to different types of data sources. For the modeled data set, well, these generally are available for very broad regions and are also publicly available. But some limitations may be on the grid cell resolution. In other words, the results may not be specific to a particular spot, but maybe for a region. And because the data are modeled, there tends to be greater uncertainty associated with the data. Regional ground-based measurements have their advantages because they measure actual conditions, but as I mentioned before, such data sites may not be close by to your own particular site of interest. And so, and there are also potentially large uncertainties associated with these databases because of the care and calibration history of the projects or of the activities if they've not been well documented. And lastly, on-site measurements are most ideal. They're customized for your particular site, for your particular project, but also they do require an investment in time and equipment in order to obtain the necessary information. Now, a monitoring program requires management activities, and in particular, someone who's responsible for conducting it. So a program manager in this case is an entity who designs and executes an objective resource assessment campaign. This can be internal to the organization responsible for developing the solar system, or this manager can be a third-party expert organization. A manager ought to be well qualified, have expertise in this type of activity, be very responsive to the needs of the program and maintenance issues as well, because data recovery is an important aspect of any field measurement campaign. And importantly as well, the manager and as well as the measurement program should be very high quality and sort of have a reputation that will achieve credibility with users, including future investors. Now, a first step in a solar resource assessment is the design of the monitoring program. It lays out the plan that defines the necessary equipment and the data parameters, as well as the instrumentation, operations, and maintenance. The most common parameters to measure are things like global irradiance, either on a horizontal surface or on the plane of array, a tilt level, direct normal irradiance, which is sort of the direct beam, as well as diffuse irradiance as well. Meteorological parameters, which are important to measure, are air temperature, wind speed, and also other parameters could be precipitation and the like. These parameters are important to help understand the relationship between, say, module temperature, if you're talking about a photovoltaic module, air temperature, and the degradation of output with temperature, and also looking at wind speeds, which have an impact on cooling the panel and thus impacting its conversion efficiency, but also wind speeds are important for engineering load evaluation for a project. The monitoring program also needs to address logistics and quality assurance. This includes defining a project manager and a project management structure so that all the staff know what's expected of them. Installation and commissioning procedures, documentation, scheduled and unscheduled maintenance, data validation and quality control procedures all need to be outlined in advance. Sensors need to be calibrated both before and after the measurement program. And data analysis for the period of record is obviously essential, as well as the correlation of your on-site data with some long-term reference station. Now, rating agencies generally expect an investment grade type of analysis for the measured data. There are some rating criteria for solar power projects that are out there. One rating agency, Fitch, indicates that the two most important third-party reports for a solar project debt rating are a third-party solar resource supply assessment and a third-party engineering report. Now, analysis needs to include sort of high-quality on-site data, so a proper investment in a measurement program is essential here. We've talked about making the projection of your short-term 1 or 2 year measurement program to what would be anticipated over the long term, the lifetime of the investment. The derivation of energy production estimates at various probability levels, both for first year and the lifetime of the project. The project performance will likely change with time, and so those need to be accounted for in the analysis. Uncertainty issues in every step of the process need to be understood and quantified, and then the P90 energy production projections for both first year and long term need to be provided as well. This graphic shows the nature of solar resource uncertainty and how it impacts the P50 and P90 values. Again, the P50 being sort of the most likely anticipated energy production from a solar project. So there's a 50% probability that the output would be greater than the number, and 50% probability that it would be lower. But P90 is a lower production number, but it means that you have a 90% probability of meeting or exceeding that value. And the goal of a measurement program is to reduce the overall uncertainty in your solar resource and energy production projection. And by doing so, you can increase the P90 value, or the long-term energy production output, because you've reduced the uncertainty. And the P90 number will actually be closer in value to the P50, which is desirable. So the figures in the scale, figures in the graphs here are to the same scale, and they represent satellite modeled data as well as on-site measured scenarios. And the table represents typical uncertainty for global horizontal irradiance using industry standard methodologies and a high quality measurement program. Sources of solar resource uncertainty, the typical ones are the type of data source used to estimate the resource, interannual variability issues, the representativeness of the monitoring period, as well as the representativeness of the site itself, or any spatial variability that may come into play. So to wrap up here, I just want to summarize that on-site solar monitoring programs can significantly reduce the solar resource uncertainty by half or more. Careful system design and operation by a qualified party is needed to ensure quality measurements that are accepted by third parties. And finally, on-site monitoring supports high confidence energy estimates on the order of the P90 values or any other probability of the value for investment grade analysis. So I thank you for your attention, and I guess I'll give controls back to Kathy.
All right, thanks a lot, Bruce. Good info. We will now move on to Peter Hoberg. Before joining Solmetric, Peter was busy gaining over 20 years experience in marketing and business development. Some of his responsibilities have included product management, sales support, and support planning for test and measurement hardware and software. More recently, he was a business development manager at a small renewable energy company, Peter holds a green MBA degree from the New College of California and has a BS and MS in electrical engineering from Stanford University. So Peter, please go ahead and share some of that expertise with us.
Great. Thank you, Kathy. And I'm going to shift gears just a little bit and discuss some topics of site evaluation that aren't necessarily weather-related so much, but we'll go through these topics. First, we'll talk about some of the terminology that's common. I realize many of you may be already familiar with it, but I'll just review them briefly. We'll talk about an example of PV system, photovoltaic system, electrical performance, and what effects different characteristics could have on that, such as temperature, wind, irradiance, shading, and soiling. And Bruce mentioned some of these. I'll cover them with a little bit different view of them. So Solmetric, just real briefly, is a manufacturer of test solutions for solar installers, ranging from site evaluation solution to some modeling software and some IV curve measurement solutions. So here's some of the terminology that is common. Irradiance is as Bruce mentioned, has many different aspects, from the diffuse to the normal, direct normal, and so it can be a complex subject in and of itself, but basically that's how much kilowatt sunshine you're getting over a given area. So it's a rate of energy. Insolation tends to be the amount of energy in kilowatt hours per some area. Solar access is actually defined as the amount of or the ratio of insolation you get given a specific shading scenario compared to what you would get without the shading. In most large systems, shading is tends to be avoided. However, it's important to take into consideration because it can have a dramatic impact. Tilt and orientation factor is how close you are to the optimal tilt and orientation. Typically, for large systems, you're going to find that that value. It is a little bit weather dependent, but typically, you know, for fixed arrays, you're going to put something south, and you're going to and you're going to put it something close to latitude tilt for optimum annual production. Total solar resource fraction takes into account both solar access and tilt and orientation factor. Obstruction elevation is also something that becomes important. When you look at the horizon, there's an angle that's described by various obstructions that could obstruct the sun, and at least from a direct normal irradiance point of view, reduce the amount of insolation when the sun is behind that obstruction. So that's another important factor. So in the course of the day here, we may have times of day where there's no access to some access, maximum, and then reduced because of obstructions or so on. This can be influenced, the arc of the sun over the course of a day, you know, with a fixed array would, you know, obviously have a big impact on how much energy can be produced. The impacts are, you know, not only the climate, but the array orientation and the shade and the soiling, etc. Obviously, the sun's path is not fixed. So because of the tilt of the Earth's axis, there is a definite difference from over the course of a year in the way the sun's path is described, and there's a lot more information on this NOAA website for those of you who want to look into it further. And you can describe that in a chart like this, which is shows the December sun path, which and the June sun path as a function of solar elevation versus the azimuth, and with 180 degrees being south and 90 degrees being east, 270 being west. and these are solar times described in the chart here. And so you can see as a function of over the course of a year, you get significant variation, and this can cause this becomes part of the calculations. For a fixed array, what you'll have is an optimum tilt and azimuth that will gather the most kilowatt hours per meter squared, or the most insolation as a function of the whole year. And as you roll off from that, you'll get a difference, which is defined as a percentage here of the total. In this case, in San Diego, 2,143 kilowatt hours per meter squared. Now, this is a typical meteorological year, and some of the other speakers are addressing, obviously how to improve on that for specific years. But this is going to be how tilt and orientation can impact energy production as well. In the case of a photovoltaic system, there's a current and voltage characteristic that looks like this, and every type of technology is going to have a little bit different spin on this. But if you look at a solar module or a string of modules or a sub-array or a whole array, it's going to have some DC current versus DC voltage, which looks something like this. It's got a plateau where current is basically constant as a function of voltage, and then rolls off where it becomes sort of this hill. So there's this plateau followed by the hill, and the power, which is the product of current and voltage, does this blue line here, and typically there's a peak in power at the max, at the knee of this curve, and that's the max power current, max power voltage, and the maximum power point where the inverter that's operating the system is designed to go. Now, as you get different irradiance on the system, different temperatures on the system, you'll get increasing, with lower temperature, you'll get more power. This hill will change its position and will go out, so the open circuit voltage, which is down where the current is zero, the open circuit voltage will increase as a function of decreasing temperature. Or in terms of, and the next slide shows if you have increasing irradiance, you'll get more short circuit current, which is the current where the voltage is zero. And so you get this curve where the plateau varies as a function of irradiance. If you have some effects of shading, and this can be even a small amount of shading, you can have a dramatic effect on the IV curve. This is an example of what can happen to this current voltage. What you're trying to do is you're trying to maximize sort of the area. If you imagine this as a rectangle, you're trying to maximize the area with the most irradiance you can get, a lower temperature, and you're trying to get the most area under that curve. And this is an example where a business card was placed on a single cell inside a string of 15 modules. And so you can see a little ding in that curve, which can cause a dramatic impact because of the series nature of the PV sort of methodology. And so that can cause a significant amount. So you think, well, in my larger array, I'm not going to have any shade. I'm not going to have that problem. Well, what's to say that a bird's not going to, put a business card size dropping on something on a module, and whether or not that gets detected and taken care of to optimize performance is, may become an important factor. So the more dramatic shade effects where whole cell strings can be damaged or impaired can cause dramatic changes where you don't see those in the current or voltage edges like the open circuit current or open circuit voltage or short circuit current, but you do see it in the curve where the power is dramatically shifted down and the IV curve has this big transition in it. And that's a little more severe shading example, which might happen when you start to either lose a cell string in a module or because of a performance problem, or a bypass diode fails, or if you start to get inter-row shading in a way that might happen towards the end of the day. So these are some shade analysis tools for looking at the environment to from the ground level to do a sort of site evaluation. And this is common to do in smaller size systems, but also larger size systems, to check around the edges of the array area and also check for shading impacts that might impair production from obstructions that are within the area of the array. This is a view of the, you can go to the next one there. Thank you, that's good. This is the approach of using a fisheye lens and a digital camera to basically take a picture as if your eyeball were on the where the array is going to be, looking straight up and seeing the whole globe of the sky, and then detecting where those obstructions will cause shade relative to the sun path for that location and making percentage calculations for that. Then you can have a strategy that might include these elements, where you might want to measure points around the array area. You might do a grid, or you might just measure the edges. You might have a maximum space between readings of something like 10 meters. And then you measure more or less at the height of the modules, and you check for worst case where you're going to get the shading, and then possibly mapping out shade-free zones. Now, no zone might be 100% shade-free, but you might be looking for shade-free within a certain time window. For example, this shows some measurements around a facility, and the little icons show where the measurements were made. You can imagine this being done in a field as well, and then taking the GPS coordinates for each measurement as you go, and then being able to look at those results. And then mapping out the shade-free zone. The red window within this fisheye picture here over on the on this one, you can look at it in a preview while you're on the site, or you can look at it afterwards, and you can see where shade's going to enter your, say, 9 a.m. to 3 p.m. window, and you can make sure that you back off of that so that you do not end up with shade inside of that that shade-free time window. So this is a way to elevate if there's a situation where you can't get the device, the measurement conveniently to where the modules are going to be before the structures exist. It's possible to raise up the measurement platform. And also, I mentioned inter-row shading. That's an important influence as well. There's a nice calculator from the National Renewable Energy Labs called the System Advisor Model, which has a way of calculating the inter-row shading based on row spacing and so on. And so that can be an important factor as well. I wanted to mention is that, here's an example of calculations. I mean, measuring shade is important, but there may be some aspects of the shade that you can calculate using tools where terrain is modeled, or buildings and trees have 3D models. And if those are available, then you can make the shading analysis through calculations, and some tools are available to do that. Those also may provide for visualization of the shade as well. One last issue I wanted to mention is that soiling is another important site evaluation criteria. Precipitation has the benefit of cleaning off modules, but having modules in a zone which is going to be dirty can cause effects where you have uniform soiling here or edge soiling here, which is brought down by precipitation to the edge of the module, and that causes a loss in the irradiance effectively that's seen by the module, and can have a very dramatic effect. And then when you replace, this is a new replacement module compared to dirty soiled modules, and that can cause a mismatch effect. And so having uniform production of clean modules is going to be important. And so choosing a site where you're going to be able to manage that either by cleaning them frequently or by having nature clean them for you is an important factor as well. thanks for your time, and look forward to the questions and answers.
All right, thanks so much, Peter. Great information. As we move on to Gwen. Gwen performs market analysis to develop relevant solar products. She's been with Tier for over 3 years. Since joining the company, she's led the effort to create the first high-res 3-kilometer global solar data set. She's also done work internationally with several public groups to define the best practices for developing large solar installations. So Gwen, please go ahead.
Hi, thank you. I hope everybody's having a good afternoon. I'm going to jump right into this. The reason we do a solar assessment and a resource assessment in particular is because we want to answer some key questions. We want to know where the best place to build a project is. We also want to know, is the resource going to be available when we need it? It's no good if you don't have the sunshine at the time of peak power rates, for example. And then you want to know what the long-term resource variability is going to be at a particular site, because you want to know, is this site going to produce year to year? One good year is not enough for a project that's meant to last 25 years. And I think Bruce covered the p-values there nicely, so I'm going to skip past that, but you can ask questions if you have them later. So, what we want to consider when we go ahead and do our site assessment is, what resource do you need? GHI, global horizontal irradiance, is the type of solar resource you're looking for a photovoltaic project, where DNI, direct normal irradiance, is what you're looking for in a concentrating or a photovoltaic array that is on a tracker. And diffuse irradiance is what you're going to get on a cloudy day. Those numbers are important, but they're not really what you're going to be looking for when you're looking for what the fuel of your project is going to be. The next thing we want to look at is, what the resolution of the data set that you're going to use is. If you have ground stations taking observations for you, that's a very high resolution. That's right at your project. But if you're going to use a different sort of data, satellite or modeled data, you need to know what the resolution is going to be. If you have terrain that is very even and doesn't change, for example, you live in Kansas, you can probably get away with a pretty low resolution data set. But if you live somewhere like California, where there is a lot of difference from place to place, you're going to want a really high resolution data set so that you can understand what the microclimates of a particular area are going to be. Then we want to look at time. 1 year of data is better than no years of data, but as you can see, in this picture, there's a lot of variability from year to year. So, for example, if we look at 2003 versus 2002, there's differences in those years as well as in the months. If we look at September versus October, we can see that October is a lot spottier, particularly year 2000 October was not as sunny as like all the previous Octobers. So you want to understand what that variability is going to be at your particular site. And so, for example, you want to put any observations you may have into context. What we see in this picture is you have a long history, and it's a fairly consistent site. And you can kind of see this gray line here. That's the 1 year that observations were taken. They happen to include the lowest values in the entire history. So if I was only taking ground stations at this particular site, my observations might say that this is a non-viable project, where the entire history says that it's probably okay, but you have to look out for a low year in particular, which is why we don't want to use TMY data to do the final production analysis of a particular site. TMY data, typical meteorological year data, is designed to be a really easy way to get a sense of a site. It's good for prospecting and getting an initial look at a particular site. But the entire purpose of a TMY is to be typical. So it erases any variability, the really high years, the really low years that you would see at a particular location. And so it doesn't really give you a sense of what the potential risk for a site is in terms of resource, and kind of, everything that you would want to know about a site before you go ahead and develop it. So we really recommend that you use a long-term resource assessment. And so what are methods for getting those long-term assessments? There are 3 ways. You can do atmospheric modeling, you can have ground station observations, or you can do a satellite-derived data set. You can also combine methods and sort of get all the pros and cons of both. So the first one, atmospheric modeling, is something that is used a lot in the wind community, but is not generally applied to solar assessments at this time. The models really have a hard time resolving cloud layers, which is really important when we're talking about solar resource, because clouds are really what are going to determine if you're getting sun or no sun. So at this time, it's not really used widely, but in a couple of years, that might very well change. Ground station assessments, where you put in an observational station and maintain it, and you get your data out of that, is a really good way of getting information. And I think Bruce covered that really well, so I'm not going to go into too much detail at this time. And then, the thing about ground stations is to get a sense of your long-term average, you really do have to take many years of data. 1 year of data is not long enough. For GHI, for PV projects, you're looking at 2 to 3 years of measurements. And then for DNI, which is a much harder measurement to take, it's going to be 5 to 15 years, which is a long time to wait before you build your project to know if it's going to be a viable site. So ground stations are great for resolving site-specific information, but just take a lot of time to get right. So another way of looking at it is satellite-derived assessments. You take satellite imagery, and what you're looking for is, are there clouds or are there not clouds? And this is a great way to get a sense of what is going on in a particular location. Satellite data is known to be really accurate, and beyond 25 kilometers of a ground station, it's probably the most accurate thing you're going to get. But there are issues with areas of high albedo, high reflectivity, also turbidity, things like aerosols and dust in the air. Snow is a great one because snow looks like clouds to a satellite model. So you want to know, was it snow or was it clouds? So what you can do is resolve some of those issues by taking in other data sets, a turbidity data set, a snow cover data set, adding that to your satellite data set, and getting information out of there that's more accurate. But you want to be able to confirm that with some sort of ground station truth. So, the great thing about satellite is you can get a nice, consistent methodology. You can compare sites anywhere in the world, and that's a really great advantage. But for a particular site, what 3-tier likes to do is combine both satellite and ground station so that you're getting the site-specific microclimate information of a ground station, and you're combining that with a long-term record of a satellite data set. And the way we do that here is through model output statistics, which is a standard methodology within the numerical weather prediction community. It's widely used in the wind space, and we've applied that to our solar products as well. MOS is a multilinear regression equation that takes leading predictors from the observational data and applies it across the long-term record, which results in a satellite record that is well correlated to a potential site. And we do that using the ground station information that you would take for a year, hopefully, to get all the seasonal effects, satellite drive data, and then also weather predictors such as temperature and humidity. We run that through the statistics model, and you get out the long-term record that your bank is going to be looking for and that you want to use for your production modeling. We have an example at Desert Rock. Our satellite irradiance data set was about 2% low at this particular location. We were able to apply the MOS correction and get out a data set that was much closer, but you'll notice is not exactly the same, and that's because we don't want to overfit to the ground-based data. Otherwise, you lose any annual variability. You just see the same year over and over again. And you don't want to do that because that variability is really what's going to tell you if this site has a good long-term potential to be a great producing site. So just to kind of wrap up, you want to do good prospecting. You don't want to use TMY data for your large projects. It's good for residential, even small commercial. But if you're looking at a project over a megawatt, you probably want to go for something that's going to be a longer-term solution. You want to collect accurate ground-based measurements. I can't stress that enough. If you do end up correlating any long-term record to your ground station data, it's only going to be as good as your ground data. So absolutely, get that done first. You want to get context of your observations. Is this a high year? Is this a low year? Is this actually a nice average year? Is really what's going to happen? And there's a lot of ways to do that. And you want to manage the risk of a project that uses renewable resources like wind and solar so that you're getting good energy production modeling, and then you have a good output to your project. Thanks for listening, and if you guys have any questions, we'll be taking them after this last presentation.
All right, thanks so much, Gwen. Again, yes, about the questions, I just want to reiterate that you can please submit any questions that you have in your GoToMeeting panel, and we will take those at the end after Stacy presents. So now I would like to introduce our last presenter, Stacy. Stacy has experience in wind and solar resource assessments. She is currently the lead analyst for solar assessments and has helped develop the solar resource assessment process at WindLogic. She holds a BS in meteorology and an MS in atmospheric science from the University of Arizona. So take it away, Stacy.
Great. Thank you, Kathy. I'm going to kind of talk about some similar points and go into detail about some things that the other presenters maybe have not. First, I'm going to talk a little about data sets. Some of Gwen and Bruce, I think, talked about these already, so I'll skim through them. But as they mentioned, you have multiple types of different solar irradiance data sets. All of them have pluses and minuses, and it's important to understand the difference between all of those data sets, and it's important to look at multiple data sets in order to determine the best resource for your site. Along with your solar irradiance measurements, it's also important to look at other meteorological variables that can affect your solar field. For example, in PV, as one of the other presenters mentioned, temperature can significantly impact the energy production you get out of your site, and there's multiple different data sources for temperature, wind speed, and humidity as well. And again, all of them have pluses and minuses and different lengths of time. And so at WindLogic, we look at multiple ones of these data sets to combine with whichever solar irradiance data set we're looking at. Wait for the slide. A little bit more about the satellite data sets. I'm going to compare this to, on the right, you have a numerical weather model that's modeling the clouds, and as Gwen mentioned, it doesn't model clouds quite as well as it does things like for wind. On the left, you have the visible satellite data set, which is the data set that our solar radiance satellite data sets are based off of. We have nothing like this available to us to use for wind energy assessments. So this is a really big plus for us to have a data set that goes measuring real-time data going back, 10+ years. As with all data sets, the satellite data isn't perfect. It's looking at the clouds, and as Glenn mentioned, it thinks snow cover is a cloud since it's currently only looking at the visible band in the satellite data set. So if you have a site that has snow cover on the ground and little vegetation, it's going to underestimate your solar resource. Currently, the best way to account for this is to have on-site measurements that you can work towards making a correction in the satellite data too. They're currently working to include other bands of the satellite data in order to help minimize this problem, something like including an infrared band into the measurements, and that'll hopefully be available in the near future. Another thing it's very important to, as the other presenters have said, to account for long-term variability in your measurements. The solar resource does not remain the same year to year and is significantly impacted by big meteorological features such as El Nino and La Nina and other multi-decadal oscillations, such as the PDO oscillation. In these plots on the top, they're the last 30-some years worth of both GHI data on the top and direct normal irradiance on the bottom. And you can see the percent change they've had from the P50 value over a 10-year period. GHI typically goes in a plus to minus 5% of your P50 over a 10-year period, whereas direct normal irradiance varies more over time since it's more impacted by cloud cover. And it ranges in a plus or minus 10% from the P50 mean. Other things to consider in long-term measurements is things like volcanic eruptions can impact your solar resource data. Back in 1992 when Mount Pinatubo erupted, there's a significant drop in solar resource data or your solar irradiance due to debris being thrown up into the stratosphere and moving around the globe. Again, this has a bigger impact on for thermal projects since it impacts DNI more than it does GHI. And whereas these type of events only occur once every, say, approximately 25 years, so they don't really impact your P50 too much, but they are events that should be taken into account into your uncertainty analysis when talking about things like P90 or P99 values. Talk a little about TMY caveats. Again, TMY doesn't account for any sort of interannual variability. And this image up here is an image from the first NREL TMY documentation they put out there. Back then it was called the test reference year instead of typical meteorological year. And back when this was originally created, it was before solar energy was popular. And so it was actually built for, as you can see in the circled area, energy conservation and energy consumptions in buildings. And then this was just the best data set available to make available for solar resource assessments when people needed something. And so it was not designed for solar resource assessments. And the weighting scheme really shows that because their weighting scheme is weighted 50% on other meteorological values like temperature, dew point, and wind speed, and then it's 25% weighted towards GHI and 25% towards DNI. And this can create poor year selections occasionally when looking at solar irradiance because just because you have a typical year in temperature doesn't mean that's going to be a typical year for your irradiance in some cases. So you'll notice in some cases you'll get anomalous weather patterns affecting your TMY properties in certain months. This is an example of where 1997 to 98 was a really strong El Nino year, and that results in cloudier years in the desert southwest areas and reduced irradiance, but things like temperature may not be as seriously impacted. And the purple line shows the METSTAT data that NREL would have selected their TMY years from. And at least at this particular station, they selected 1997 during the winter when El Nino is typically the most present as one of their years at that station. This can result, if you look at the month-to-month basis, an underestimation of the resource at that site during that month. This can happen in any month. So for example, in Arizona, where you have the North American monsoon, you should make sure that they're picking a typical year in those monsoon months. So how do we work towards a bankable assessment at WinLogix? I'm going to kind of go through some examples. This is an example PV site in Southern California. So we would ingest any ground data available. Preferably you'll have data available for a year or at least covering multiple seasons so that we can compare that with our satellite data and other MET data that we're looking at. Then we'll look for any biases in the data, whether it be annual biases or seasonal biases. We also take into account biases, especially due to clear sky days, because when you're looking at your satellite data, it's on a higher resolution or a lower resolution than, let's say, your ground data is at. So unless your ground data is in the center of your satellite pixel, you're going to have differences on cloudy days as clouds move slightly differently through the different sites. So we focus on especially making sure that on clear sky days we're accurately capturing the irradiance value. Once we have our satellite irradiance data set picked out, we want to look at, as Peter mentioned, site-specific issues. We look to make sure, see if there's any mountains nearby and if those features could potentially shade our field, our solar field. In the picture on the right, the area in the yellow is that sun angles, as Peter mentioned, and the area in the gray at the bottom represents mountains. So at this site, you're going to have shading due to mountains in the afternoon at your site. Also need to account for soiling losses. How's your panels going to get cleaned at the site? How often do you have precipitation? Are there things like farms nearby where during certain seasons when the farmers are tilling up their fields, could you potentially have more soiling loss because of that? Also need to account for air quality, which could affect your satellite measurements and your on-site measurements, and potentially your solar panels and soiling. After that, you can work towards creating your own TMY type file. You can base it, we recommend basing it solely off your solar irradiance for whichever type of solar project you're building. So that would be solely off GHI for a PV field or DNI for any type of CSP plant. Then you can compile an 8760 of your resource on a P50 or P90 basis and take the overlapping temperature, wind speed data for those same years that you picked for your TMY. This helps minimize any potential poor years selected in other types of where they have a weighting methodology. So in this picture on the right, you have GHI on the y-axis and months on the x-axis, and the dashed lines represent the individual years in our satellite data, and the blue line represents the P50 that we would have chosen based solely off of our GHI data, and you can see that falls directly in between the range of the individual years. Whereas the TMY3 station, at least in June, you can see falls higher than any of the individual years' worth of data. There's still a disadvantage to this. You're still only accounting for variability in one variable, which is your solar irradiance, and this is the most important variable when talking about solar resource assessments, but variability in temperature, especially for PV, still plays a part. So how does this play out? This is an example from a thermal site. You can see our P50, P90 that we would have created, but then you have ground measurements, which are the blue line, which had the same solar resource as that P90 profile. But when you run those through energy production calculators, the P90 we created was over 10% different in energy production compared to what the ground showed, even though they have the same annual average solar resource. The best way to get around this is that it's preferable to run all of your data through your performance models to get energy production results. When you do this, you can see the variability in your energy production. So you bring these into whatever type of energy prediction software you prefer, whether it be PVSys, SAM, which is the NL Solar Advisor model. Some people have their own calculators they like to use. And then you combine this with your site-specific information, and it's all driven by your solar resource file. It's important to understand the caveats of the prediction software you have. There's usually a lot of different inputs that go into these, so it's important that you understand all of them and that the person running it has experience in those tools. Then once you run all those years through, you can get your uncertainty analysis and your predictive intervals, and all that's going to be now based solely off of one variable, your energy production. And as you can see in the picture on the right, you can look at them both on a monthly basis or on an annual basis. And in this case, in the monthly, you can see that the area in the summer has much higher variability than your months during the winter due to the influence of North American monsoon in the southwest. And just to wrap up some points, solar resource is much less variable than a wind resource, if you're familiar with wind resource, but the variability in solar is still important to take into account. And as other presenters have mentioned, there's no single source of truth in any data set, so it's important to look at multiple data sets to determine which one's best for your site or combine methodologies to produce a bankable assessment. You might also consider other meteorological variables that could affect the quality of your data or affect energy production of your solar panels. And always use the TMY data with caution. It is very easily accessible and easy to use, but it's not going to produce uncertainty and variability for you in your analysis. And that's all I have. Thank you for your time. I'll pass it back to Kathy.
Okay, thanks so much, Stacy. And now I'm sure after all the information, the audience has some questions, so we'll begin with those. And actually, Stacy, this one's for you, so I'll direct this right towards you. Is there a standard file format for the 8760 TMY file that you had mentioned, or a predefined way to share the information?
We have people that want to look at it in an 8760 format, which is just like an average file. So it's a 1 year and hourly format. Some people like to look at the final results in like a, what we call a 12 by 24, which is like a P50 file for, you know, time, hours in a day versus each month. So it really depends on what person is looking. We can put it in multiple different formats.
Okay. And then I think Bruce and Gwen, I know you mentioned this, and we're wondering if you mentioned a lot of the site assessment had come from sources and wind assessment as well. Just wondering if there's a correlation between those two. Is the technology usually produced for wind first and then solar, or how does that kind of work? Anyone can answer this.
Well, this is Bruce. Sort of two aspects to it. Certainly on the measurement side, they're fundamentally different. You know, what you're measuring, how to measure. I think the question might deal more with the ability to model or estimate local solar conditions from other existing data. And I think, as you heard from at least two of the speakers, sort of conventional modeling tools in wind aren't as applicable for solar because of the challenges of modeling cloud layers, and so having a combination of measurement and modeling is the more robust program. So there's some similarities because they're both meteorological phenomena that you want to characterize accurately in terms of space and time, but just the ability to do so with high degrees of accuracy bring different challenges.
Okay. All right. Another question we have is, how do you use this data to determine the best type of technology, whether it's concentrated solar, just PV? How do you go about doing that?
This is Gwen at 3-tier. One of the ways you could do it is, most people come into it, I think, knowing what type of project they're interested in, given their site constraints. Mm-hmm. But if you're really looking at a site and you wanted to determine that based on a solar resource, you'd certainly look at, do you have more like higher values in GHI or DNI, which would help determine which technology you'd want to use. And you would also maybe want to look at what the patterns are on a monthly or daily basis to see, are you going to get that type of power at the times of day you're most interested in it, would be another way to look at it.
All right. Did anyone else want to add to that question?
I'll add on. I won't focus. We have a lot of people that kind of ask us what's the best PV technology to use. So you're using the same resource, but is going like a CAD-TEL panel going to be better than a crystalline panel? And sometimes that's like where temperature comes into play a lot, because like CAD-TEL type panels have usually lower temperature coefficients, so they're less affected than like a crystalline panel might be. So those are other things you can consider as well.
Okay. This is an interesting question too. Someone's wondering, how far back is quality satellite data available? How long have they been taking that kind of satellite data?
They've been doing it for a really long time. I guess quality would maybe be the hard one to make a call on. The satellites, the way they take measurements has changed pretty dramatically over the years. And you'll see jumps in technology where, they put up a satellite in the 90s that was just entirely calibrated differently than the previous ones. And so you can't really necessarily compare, like you'd have to do some really funky equations to be able to get a consistent measurement between the two. We went back to 97. Certainly, I think back into late 80s, early 90s, I would probably trust satellite measurements like over the U.S., for example.
Okay. Peter, I'm going to direct this one to you because we haven't heard from you in a little bit. Is there any value to providing forecasts of energy production for the next day or week?
Yeah, actually that question is something the other speakers might have more information on, but it seems like I heard recently that in Italy that energy producers actually get a rebate from that is provided by the utility if they can provide forecasts within 24 or 48 hours and there was an accuracy goal of 5% or something like that. And I was just curious, about that. If Italy's doing that, is that something that's a trend that we see happening in the U.S. as well? So maybe there's some other speakers that would be able to address that.
Sure, that sounds very interesting. Does anyone else want to answer that question?
Yeah, this is Bruce. I know I could speak for the rest of us. Our groups all are involved in forecasting the needs of utilities and the transmission system operators to understand what all the generating resources will be in the future, the next few minutes to the next several hours, the next several days. All those are required to operate the grid cost effectively and reliably. And there are new rules coming into place in some states that would require solar systems to provide forecasts to the transmission system operators or the local utilities so that they can schedule all their generation. And so the need for this exists already in, say, California. And so projects of various sizes are going to have to begin providing forecasts, and the solar systems also will need to be monitoring the real-time conditions, not just their output, but also the solar resource, and delivering that information to the independent system operator, the ISO, who then can provide that information to the forecaster. So just like the wind industry and conventional generation, the need to forecast is growing, and it's just part of the integration of renewables into the electric grid.
All right. Okay, we'll do a couple more questions here. Someone's wondering, is the TMY3 data useful for relatively long-term estimates of production and only kind of not suitable for estimating year-to-year variation and evaluating that risk?
Well, I'll try and answer that question. One thing you really have to consider with your TMY3 is how far away it's going to be from your site. Sometimes there's ones within a few kilometers of your site, but sometimes there isn't a TMY3 station available for within like 100-some kilometers of your site. And in that case, the solar resource, even if they're picking representative years for each month, may not be representative of your site that's 100 kilometers away, which could be on the opposite side of a mountain range, etc. So in order to gauge like a prospecting type, if it's prospecting appropriate for like a long-term estimate, you definitely have to take into consideration how far away your site is from the station.
All right. And we'll just end with one last question here. Other than solar irradiance, what other weather variables should strongly be considered in a site assessment?
This is what it's here. We like to also include temperature data, which is very important for your PV cells, and humidity, which is very important for the CSP. But everybody needs kind of all of those. Also, wind speed. If the winds are too high, that's going to really affect your panels and equipment.
All right. Okay. Did anyone else have anything to add? I think we're reaching the end of our webinar here. All right. Well, I think that's all we have time for today. But I would like to take time to thank all of our presenters for being here to share what their site assessment expertise with us. And thank everyone in our audience for listening and asking great questions. We hope you enjoyed our presentation. And Solar Power Engineering will be doing webinars monthly, so keep an eye out for more to come. Thanks, everyone.